Hi, morning there students. Right, so today we try to move away from indoors and hopefully you find it a little bit more appealing and not so boring. Okay, now let's move on to the last subtopic of your chapter 2, that is 2.4, slope stability. This should be interesting because we see slopes all the time, and hopefully after this subtopic you would look at slopes differently and you wouldn't just say tanarunto, you would use terms like not even landslide. I mean, you probably use terms like instability, sliding forces, driving forces, pore pressure, and things like that. Okay, right. Okay, here we go. Now, when we talk about the types of slopes, generally there are just two types. One are the infinite ones, as you can see in the diagram here. That is as if there's no beginning, there's no end, and it's parallel all the way. And usually these kind of slopes will be natural, as you can imagine. And the second type of slopes is the finite slope. And as I have sketched it out for you here, they may be undulating, right? But every single one, you could define where is the top and where is the base, right? There's a top, there's a base, and there's a finite or definite height to each slope. And usually these are the ones that are either man-made or they are being created from natural situation. For example, you cut off mountains or slopes into slopes to form highways, dams, and things like that. Right. This is an example of a natural slope failure. As you can see, there's a lot of vegetation on here, right? And you also can see from here that the vegetation are actually very superficial, just on the surface of it. So be very careful when we talk about vegetations or plants being able to prevent landslide or slope failure, because a lot of times the vegetation is only on the surface. It probably doesn't go any deeper than half a meter or 1 meter. So as you can see, when the failure is deep-seated, vegetation on top is not helpful. Maybe sometimes it's even a harmful one. You can read up more about roots drying up the soil, desiccation, and things like that. Okay, some other examples. On the left, you can see this railway embankment that has failed, and you can also see that there used to be a retaining wall along here, and it's gone as well. So if you recall, when we were talking about learning about lateral earth pressure in the previous lesson, we did have an example of a railway embankment failure, and I did tell you that sometimes it is a combination of lateral force pushing off the embankment, and also a factor of slope failure. So this is a typical example. As you can see, the rail tracks are running across the slope. So this is a natural slope hill coming down, and we actually cut off this part to become flattened so we can build the railroads. But at the bottom of it is still the continuation of the slope. So this could be a failure that is deep-seated, coming down from the top and causing the embankment to be swept down. Alright. Another example here, this was a picture taken in Taiwan. This kind of earthquake taken from an aerial view, you could see that it's massive, alright, coming down from the hillside, and this could be translational, as you can see later on, the definition of it. And the last one here, nearer to us, Kelanja in 2004. Obviously, this is a rock fall, right? On the side of the highway, you could see these are actually very vertically cut rock surfaces, alright. Okay, now according to the United States Geological Society, USGS, these are the definitions of slope failure that we can have. So you can see rotational, translational, block side, so on and so forth. And maybe sometimes it's difficult to classify them as one. Sometimes it's a combination of one or two or even three. Right? And in geotechnical engineering, typically we'll just say that they are either rotational slips or translational slips, or they are a compound slip, right? As simple as that. If they are rotational, as you can see, it can be circular. It could be non-circular, meaning that this is some kind of curve, but it's not part of a circle. It could be translational. This is for infinite slope. The whole bulk of the soil mass is going down, sliding down like in a slide. And it could be a compound situation. This part could be circular, but the bottom bit could be a non-circular one. Alright. Now let's look at the slope stability analysis approaches that we have that could be used to analyze your slopes depending on the situation. Right, first let's look at the infinite slope. So remember, infinite slope, it's almost as if there's no beginning, there's no end, and you're looking at just one portion of it. So just let's look at KLMM, just this section of it, right? If you take it down, you could actually redraw the forces acting on this particular slice or this particular section into a vertical force that's coming down, that's W. That's the most basic force coming down because due to the self-weight of the soil itself, right? W. Now, remember your force vectors. If I try to derive the vertical and the horizontal components of this force, I could do this. W, if I close this angle of I is cosinus, right? So I'll get a vertical force acting on this surface, alright? And that will be my normal force. So this normal force is alright. It's not going to cause any instability to the overall infinite slope because why? It is being supported by the base, as you can see here. And mind you, the I angle here that we are looking at is actually the gradient of the slope, right? This I. Now what about the force when I open it up and make it into the horizontal component, right? If you can't quite see this W sinus I being opened up here, is parallel to this blue line. If you open up the angle I, it becomes W sinus I, right? Okay, go back and check up your trigonometry if you have forgotten about this. So W sinus I is the one that is dangerous. That is a driving force that is pushing, alright, pushing the slope down, obviously, okay? And who is going to stop that from happening? Yeah, right, there's a shear force coming down from the base, Mn. So, in other words, you could see that it's the shear strength of the soil at the base of this sliding surface that is going to provide resistance against the driving forces. Okay, now consider a situation now, the same infinite slope, but now we have water coming through. Now, I say water coming through, I didn't say static water. Alright, so when there's water coming through, that's when the problem will start coming in, because when water is flowing in the soil, there is a water pressure. We call pore water pressure rather, right? So again, infinite slope, but now you see squares in there. These squares are actually made up of flow lines in this direction. Can you see? Flow lines. And you have equipotential line coming this direction. So you are right, they are perpendicular to each other, berserenjang. And these are actually components of a flow net. You can Google that up if you want to. So flow nets are simply drawn to assist us to determine the seepage, water seepage through soil. Okay. So for now, let's just focus on A, B, C, D. Just two squares of it. Alright, and and this ABCD rectangle it has a dimension of B multiplied by D. Got it? Okay. So now, first and foremost, we need to know what is the soil weight, of the element ABCD. So there's W there, and the driving force. Remember, the driving force is at the base here, W sinus. So W sinus, W is gamma dB, and the normal force acting down here, that is your W cosinus I. Remember, this is about water seepage, so the pore water pressure is going to be bad, adding on to the forces pushing the soil down. So in this case, as you can see, there's a piezometer being popped here so that we can know where is the groundwater table in a vertical manner. So vertically, the distance will be D cosinus I. This is all trigonometry. You can derive that if you want to. And U, that's the pore pressure, is gamma W D cosinus I. Simply gamma, again, multiplied by the distance. Similarly, when you did for the soil weight causing the driving force and also the normal force. Alright? When you put them together, you see it is actually B multiplied by gamma W D cosinus I, where whatever that's in this bracket is actually the pore pressure as shown in the diagram. So in this case, when you have water seepage, for the slope to fail, alright, you need to, the tangent of your gradient angle has to be a portion of your tangent phi. Remember, phi is the friction angle of the soil. That is giving the shear strength of the soil. So in this situation, obviously, the soil is purely granular. It's sand because you don't see any C component here. There's no cohesion. And I said a portion of the tangent phi. Why? Look at this. The gamma that you're using here, gamma T, that is the actual gamma of the soil, has to be minus off with the gamma W, because the water is not contributing. It's actually detrimental to your slope stability. So this is a simple formula that's being used. Okay, more details about how the formula is being derived can be found in your module if you like that. Okay. The next method is the Taylor stability number. So this is actually quite a simple approach to use, provided we understand how the chart is being used. So this is a formula. NS is simply the stability number. CR, C is a cohesion, that's the strength, but R here is indicating the minimal shear strength that's required to keep your slope safe. So anything beyond the number, beyond the shear strength, the slope will start to be mobilized. In other words, it will start to move. When it starts to move, that's when your failure is being initiated. Gamma at the bottom, obviously, is your soil's unit weight, and H is the height of the slope. H is the tricky one here, as you can see in reading off the chart. So now, let's take a look at this diagram first. This is the cross-section of your slope. There's the base, that's the top of it, right? Sometimes we call it the crest, C-R-E-S-T. Top of the slope, bottom of the slope. So this difference of these two levels is the H. And there's another level you need to know, that is from the surface of your slope, or from the crest to the hard layer. Alright, that is DH. So if I know H and I know DH, can I find D? Because you need to have D in order to read off the chart. Alright, take for example a simple one. Say my H is 10 meters and DH is 20 meters. So my D automatically will be 2. So I just need to read off from this column 2. And what is the beta angle? The slope angle of the problem concerned. Just read off, say it's 60. So I go through here, come to 2, I get 0.191. So that will be my Taylor's stability number. And the last method that we would like to look at is actually the method of slices. This is again very common, and it's graphical. So provided you like to draw, and provided you know how to draw it correctly, so this is how it works. As you can see again, there's our slope, the base, the top, and this is actually part of a circle. And this is the center of the circle. So you could see from this diagram here, it could be anywhere. So yeah, right. We call them the trial circles. You could put your the center here, and the circular arch will be somewhere around here. It could be anywhere. So in reality, when we try to analyze a slope stability using the method of slices, we would actually be making trial circles until we find the most likely place where the failure surface may take place. Alright, so important thing here is to bear in mind is part of a circle. Okay, and method of slices, as the name will tell you, you need to slice it up into equal elements. So everyone is almost rectangle. Can you see? It's almost rectangle. You just assume this is a straight line as a rectangle, or if it's not a rectangle, it will be what? Almost like a trapezium, or sometimes it could be a rhombus. But the ends, look at this. The ends will be something that's almost triangle. Bear that in mind, okay? And now let's look at an individual slice, the forces acting on it. Again, the self-weight of the soil, W, the load coming down from the top, external load, and on each opposite side, the sides of your slice will have a normal force and a shear force. And at the base, if you have water pressure, you have groundwater table, then you have a situation of water pressure coming in, PW. And again, the resisting force is actually your shear force at the base of your every individual slice, right? As you can see, there are too many forces acting on your on every single slice of your every single slice that you derive from your circle, the circular arc that you produce for your slope. So when there are so many, it becomes indeterminate. You learn in static, one too many, it becomes indeterminate, and it becomes very complicated to try to get the answers. It's like persamaan serentak, 2 unknowns is easy. More than 2, 3, then you start to have funny equations coming in, or funny graphical method. So in order to counter that, Fillenius in 1927, he's a Swedish guy, he came up with a simple assumption. Just assume that the value of each interslice force is 0. So once you do that, being simplified to equilibrium of 0, total force 0 for each side, so you could simplify them, and it comes T is W sinus alpha, P is W cosinus alpha. So that makes it determinate. So simply put now, your safety factor, alright, for the slope will be, this is a driving force coming down, and the resistance force. So it's just a matter of how much of resistance over how much of driving force. So obviously it has got to be more than 1. If not, it is not going to be safe, right? And for your driving force, there is T, it's down here, but for the resistance force, it's actually the P force, that is your normal force acting at the base, multiplied by the tangent phi. So again, you can see it is actually deriving from the shear strength of your soil. Alright, so let's pause a bit before we go on to the examples.